In 2023, Tesla announced that its next-generation electric motor would eliminate rare earth metals entirely. For an industry built on these materials, the implications were immediate. But Tesla isn't alone in this pursuit. BMW, Mali, Renault, and others have been chasing the same goal for years. So what exactly is happening? How does the technology work? And why should the average car buyer care? Every electric vehicle motor needs magnets. The most powerful ones are made from rare earth elements, specifically neodymium and dysprosium. A single EV motor contains 1 to 2 kilograms of these materials. They make motors compact, powerful, and efficient. Nearly every major automaker has depended on them for years. But that dependence created serious vulnerabilities. Supply concentration. About 60% of rare earth mining and 90% of processing happens in China. Regardless of where a car is built, its motor is tied to a single country's supply chain. Cost volatility. In 2011, China restricted exports and prices spiked over 700%. According to Adamas Intelligence, rare earth magnet materials for one EV motor cost between $60 and $200 depending on market conditions. That unpredictability ripples directly into vehicle pricing. Environmental damage. Rare earth mining produces radioactive waste, contaminates water sources, and strips topsoil. The Bayan Obo mine in Inner Mongolia has created a toxic waste lake spanning over 10 square kilometers. For an industry built on environmental promises, this has always been an uncomfortable contradiction. Geopolitical risk. For the US, Europe, and Japan, dependence on a foreign-controlled supply chain for a critical component represents a strategic weakness that deepens as trade tensions escalate. These problems made rare earth dependence one of the most pressing, unsolved challenges in the EV industry. At its March 2023 Investor Day, Tesla's powertrain team stated their next-generation drive unit would use a permanent magnet motor requiring 0 rare earth elements. VP of Powertrain Engineering Colin Campbell described it as a ground-up redesign. But Tesla didn't invent this idea. BMW's 5th-generation eDrive, already in the iX and i4, uses a wound rotor motor with significantly reduced rare earth content. German supplier Mali developed a completely magnet-free motor. Renault and Valeo use an electrically excited synchronous motor in the Zoe and Megane E-Tech that avoids permanent magnets entirely. Toyota has explored ferrite-based alternatives. Even BYD has been researching rare earth reduction. What makes Tesla's announcement significant is the combination of ambition, elimination with no claimed performance loss, and Tesla's manufacturing scale. A critical caveat. This motor has not yet appeared in a production vehicle. No independent benchmarks exist. What follows is based on Tesla's stated goals and established engineering principles, not verified production data. In a conventional EV motor, the rotor contains permanent magnets made from rare earth metals. These provide a constant magnetic field passively. The stator's copper coils create a rotating magnetic field, and the interaction between the two spins the rotor, driving the wheels. Going rare earth free means replacing that passive magnetic contribution without sacrificing output. There are several approaches. Switched reluctance motors use shaped iron rotors with no magnets at all. They're simple and cheap, but historically noisy with less smooth torque. Wound rotor synchronous motors replace permanent magnets with electromagnets, generating magnetic fields on demand. BMW and Renault already use this approach. The advantage is precise control. The disadvantage is added complexity. Hybrid designs combine reluctance elements with weaker but abundant ferrite magnets, managed by sophisticated control software. Tesla hasn't disclosed its exact architecture. Based on patent filings and analysis from engineers like Sandy Munro, Tesla likely uses a hybrid approach with advanced inverter control, adjusting current timing and intensity thousands of times per second to extract maximum performance from non-rare earth components. The key insight is that advanced software and power electronics are compensating for reduced magnetic strength. The innovation is as much in the control system as in the motor hardware. Trade-offs exist. Without neodymium magnets, achieving the same power in the same size is harder. Control systems become more complex. Electrically excited rotors generate additional heat. Efficiency curves at partial loads may differ. These are engineering challenges, not deal breakers, but honest assessment requires acknowledging them. If Tesla delivers, the practical impacts converge on three things buyers care about most. Range. A more efficient motor wastes less energy as heat, meaning more battery power reaches the wheels. Even a 5% efficiency gain on a 400-kilometer range vehicle adds roughly 20 kilometers. Cost. Rare earth magnet assemblies account for an estimated $100 to $300 per motor. Eliminating them reduces material costs and removes exposure to price swings. When one major manufacturer cuts costs, competitive pressure forces others to follow, driving prices down industry-wide. Bloomberg New Energy Finance projects EV price parity with combustion vehicles between 2025 and 2028. Rare earth elimination could accelerate that timeline. Durability. If internal heat decreases, bearings, insulation, and windings degrade more slowly. The car performs more consistently over its lifespan. However, if new wear points are introduced, the equation shifts. Production verification is needed. The net effect, if realized, is a vehicle that costs less, goes farther, and lasts longer. That combination addresses the three biggest barriers to mass EV adoption. BYD's position is strong, but not untouchable. BYD's dominance comes from its blade battery technology, extreme vertical integration, manufacturing scale, and labor costs, not primarily from rare earth access. A rare earth-free motor doesn't collapse their business model, but it does erode one layer of strategic advantage and level the playing field in one specific dimension. For the US and Europe, this aligns with existing policy goals. The Inflation Reduction Act, Europe's Critical Raw Materials Act, and the European Green Deal all target supply chain independence. Motors built from abundant materials support domestic manufacturing without foreign sourcing vulnerabilities. For emerging markets, cheaper motors with simpler supply chains make local EV manufacturing more feasible. Countries don't need rare earth deposits to build motors that don't require them. The broader shift is that competition moves from material access to engineering capability. The companies that win won't be those with the best mineral supply chains, but those with the best design, software, and systems integration. The environmental benefit is real. Eliminating rare earth demand reduces mining damage, radioactive waste, and water contamination. But it doesn't solve everything. EVs still require lithium, cobalt, and nickel for batteries. The strategic benefit is equally real. Removing a volatile, geopolitically sensitive input gives Tesla cost predictability, manufacturing flexibility, and supply chain independence. These motivations aren't contradictory. The strongest business strategies align profit with broader benefit. The question isn't whether it's one or the other, it's whether execution matches ambition. And healthy skepticism is warranted. Tesla has a history of ambitious timelines that slip. The Cybertruck was announced in 2019 and reached initial production in late 2023. Until independent testing confirms performance claims in production vehicles, this remains a promising projection, not proven reality. Rather than speculating about the future, here are concrete indicators that will determine whether this technology delivers. 1. Production timeline. When does the first vehicle with this motor reach customers? The expected platform is Tesla's next-generation affordable vehicle. 2. Independent testing. Results from organizations like Consumer Reports and Monroe and Associates will confirm or complicate Tesla's claims. 3. Competitor responses. How quickly others accelerate their own rare earth-free programs signals how seriously the industry assesses the technology. 4. Pricing. Does the cost reduction translate to lower vehicle prices or just higher margins? 5. Rare earth recycling. Companies like Urban Mining Company and REE Tech are advancing recycling technology. If viable at scale, recycling offers a complementary path to supply chain independence worth tracking alongside motor redesigns. Tesla's rare earth-free motor addresses real problems: cost volatility, supply chain vulnerability, and mining damage. But it isn't a miracle, isn't exclusively Tesla's idea, and isn't yet proven in production. What is genuinely significant is the direction. A future where EV motors are built from abundant materials, manufactured anywhere, and priced for everyone. That future isn't guaranteed by one announcement, but it's closer than it was before. If you found this useful, subscribe. We cover EV technology and industry shifts with detail and honesty. No hype, just clarity.